First, maybe what is the first component that we're going to build?
Okay, yeah. So the starting component, well, the first component we're going to start with is the power regulation, power system.
Right.
The reason why we're starting with this is because this power regulation block is going to be used for every single further
so we can't do any of the rest of our project without power.
Exactly. Yeah. Everything needs power to run.
That checks out.
First thing we need to do is we need to look at the data sheet for the voltage regulator. So this is the first page of the voltage regulator's data sheet. And this little guy is the chip that we're looking at. That is our LDO. So when we're going to look at what the LDO can do, the first thing we want to look at is the output voltage, which is stated just here. And in particular, this states that we can do an output voltage of 5 volts. And the reason why we picked 5 volts for this circuit is because our microcontroller, the reason why we picked 5 volts is because the microcontroller we've selected requires 5 volts to operate. In addition to that, the temperature sensor and the signal conditioning circuit all require 5 volts. So when 5 volts is what we call our system voltage. It's the voltage that our system runs on. So we've picked an LDO that can produce the 5 volts that we need.
Yep.
And the package we've got, and you can see, if we hold it up to the camera, see the package that we've got here is like a little D shape. And that is a TO92 package, is the technical term, which is this one. And now if we look at the actual shape of the package, we can see one side is curved and one side is flat. And then if we hold the flat side up so that it lines up here, you can see the pins line up. So the 3 pins we've got are the output, ground in the middle, and then the input on the right. And they line up with the 3 pins that are on the chip. So the next thing we want to look at is the next page of the data sheet. And this is what states some of our electrical characteristics of the chip. And in particular, the first thing we want to look at is the absolute maximum ratings. This will always be at the start of the data sheet. So this tells us what the absolute maximum that the chip can do is. So in this case, the absolute maximum input voltage that we've got for this chip is 35 volts. That means that if we put higher than 35 volts into this chip, it's probably going to blow up. And if any of you have a lab power supply and a few spares, you're more than welcome to try. Should be pretty fun. Sometimes they explode, sometimes they just let out the magic smoke. But in this case, we're not going to be using 35 volts. We're going to be using our 9-volt battery. Okay, so the next thing we need to look at is the dropout voltage for our LDO. Now, LDO stands for low dropout voltage regulator, which means that the dropout voltage is fairly small, but it's not 0. So in this case, the dropout voltage here is this value here, V in min, and it says next to it, minimum value of input voltage required to maintain regulation. And what that means is that that is the minimum voltage we have to give the LDO for it to regulate the output to the level it says. And that value is shown in the typical column to be 6.7 volts.
Right. So we've got to give it more than 6.7 volts if we want it to give us 5 volts back.
6.7 is the minimum voltage we can put in, which means it has a dropout voltage of 1.7 volts because 6.7 minus 5 is 1.7.
Gotcha.
Yeah. And obviously our 9-volt battery is a lot higher than 6.7, and this will discharge down to, say, roughly 4-ish volts when they're fully discharged. At the point where it hits 6.7 volts, the LDO will stop working, and then the rest of the circuit will stop as well. The other thing we can see on here is, again, we can see our VO, which is our output voltage, and that's stated to be typically 5, but it can be anywhere from 4.8 to 5.2 volts. Now that range is fine to work with. The microcontroller and the sensors we've got are fairly tolerant, but in some systems, if you need a more accurate voltage, say if you're using it as an analog reference voltage, then you'd need to have a more accurate voltage converter.
Right.
So the third thing we're going to look at is the circuit and the typical applications. So this, I believe, is page 7. Now in this document, so this big circuit is actually what is inside this little chip. That's how it functions. But what we care about is the typical application circuit indicated at the bottom, which has got fixed output regulator. So we can see it's got input, which will be the input from our 9-volt battery. And we've got our output, which is our output to the rest of our circuit. We can see that the box here is the LM78LXX, which is our voltage regulator. It's got the middle lead, which connects to ground. And then, in addition to that, it has two capacitors. So it's got C1, which says 0.33 microfarad, and it's got C2, which says 0.01 microfarad. Now these capacitors are standard values, so we've got these two capacitors here. Now in order to work out which capacitor does what, you can either remember or you can look at the numbers that are printed on them. It's fairly hard to see because they are small. I don't think the camera's going to be able to focus on them. However, the one with the slightly shorter legs here says 334, which means that's our 0.33, because the way you work it out is it's a 3, 3, and then the 4 is how many zeros are on it, so it's a 0.33. And then we've got a 104, which is again a 10, and then 4. So that's a 0.01. So these three parts will go together somewhat like this. And the battery will go on the input. And then we should be able to measure our output, and that will be our 5 volts.
Cool. Shall we give it a go?
Yeah, let's transfer this to a breadboard. Okay, so we've got our breadboard. The first thing we do is talk about how breadboards work.
That's, yep.
Yeah. Because there is a certain way that things connect on a breadboard. So on a breadboard, we've got a series of holes. You can see here it's marked. Our rows across are marked by letters, A, B, C, D, E, F, G, H, I, J. And our columns are marked by numbers, 1 through to 65-ish. Now, the way a breadboard connects together is the 5 holes are all connected as one, so is one big block. So we've got 1, 2, 3, 4, 5, and they all connect together. And then the next set of holes across, we've got 1, 2, 3, 4, 5, and they connect together. And then on and on and on and on until we get to the end. 1, 2, 3, 4, 5, and they connect together. And it's the same on the other side. We have 1, 2, 3, 4, 5, and they connect together. And they're not connected in the middle. And they're also not connected row by row. So if you want to connect two things together on a breadboard, you need to put them in the same row of 5. And if you've got more than 5 things to connect together, then you can just connect this row of 5 to another row of 5, and then all of a sudden you've got all these joined together as one circuit. So say in the case that I wanted to put something in row 1 and I want to connect it to the row down the end here, I could plug a wire into here and then connect it to this one, and now these would all be electrically connected. In addition, if I wanted to connect something across the breadboard, I could plug a wire into here and then put it into this one, and then these 2 rows would be electrically connected.
Cool.
Okay, so now that we know how the breadboard works, we can start by plugging our parts in. So the first thing we want to do is we want to take our LDO and we just want to bend the legs out a little bit so they fit into the breadboard holes. So it doesn't take much force, very gently. We can bend them out and splay them a little bit. And then we can place the LDO into the breadboard in any 3 rows. So the reason why we place it across again is so that the legs aren't connected together. If we were to take it off and place it like this, horizontally, all of those 3 legs are in the same 5 holes, which means they're all connected together. And that means they're shorted out, and if you power that, it'll probably blow up. So we put it crossways, and in this case, I've got the flat side facing towards me. And we can go back to our data sheet, page 1, and we can look at how that corresponds to our holes. So we can line our data sheet up, let's say, with how it looks on our breadboard.
So that says bottom view. Does that mean we need to, is that looking up?
Yep, that's exactly right. So where it says bottom view, it means we're looking at it from the bottom, basically from underneath the part towards the bottom, and the legs would be coming out of the page here, like we had before. So if we think about it on the breadboard, it would be like looking at it upside down. So when we line up this leg with this part of the breadboard and then we flip it over, it's reversed. So in this case, our output pin is on the left side here, and our input pin is on the right side, and our ground is in the middle. So the next thing we can place in is we can put in our capacitors. So we'll go back to page 7. So we've got our circuit diagram. Place that next to it. So now we can see again. So we remember that we've got our input on the right and we've got our output on the left. And on our diagram here, the input is on the right and the output is on the left. Which means, yes, that is correct. So for the input side, we have our C1 capacitor, which is 0.33 microfarad, which is this capacitor here. Now, for these capacitors in particular, we're using ceramic capacitors. Now, these are what's called non-polarized. A polarized component is something that can only have electricity flowing through in one direction. So if we were to think about it, a battery is polarized because a battery has a positive and a negative side. A ceramic capacitor is not polarized, which means it doesn't have a positive or negative side. And you can put it in, it doesn't matter which way around you put it in, it'll work fine both ways.
Right.
If we were to put in a capacitor such as a tantalum capacitor or an aluminium electrolytic capacitor, those are polarized. They have a positive and a negative side. And if you put them in backwards, they blow up.
I'm loving how much stuff can just blow up if you do it wrong in this process.
Yeah, it's fairly exciting. Trust me, the first time you blow up a tantalum capacitor, you'll remember that they're polarized. It's fairly exciting. Okay, so now that we've put our LDO into the breadboard, the next stage will be to put our capacitors in. So we've got our typical application circuit here, which indicates that our C1, our input capacitor, remember the input of the LDO was on the right. Our C1 capacitor connects between the input pin and ground. So we take our capacitor here, and we can work this one out by it says 334, which indicates our 0.33 microfarad. Now this capacitor will connect between the input pin, which is on the right of the LDO if you're looking at the flat side, and the center pin. The center pin is the ground. So we can connect it between the two rows that are there. That will go nice and close between the two rows. So we've connected our capacitor in to between the ground pin and the input pin on the LDO. The second part we need to connect is our output capacitor, which is indicated by C2. This is 0.01 microfarad. In that case, we've got a 104, which corresponds to 0.01 microfarad. Now this capacitor, much like the first one, goes between the ground pin and the output pin. So that we can connect between those two terminals on the breadboard. And we'll just make sure they're all standing up nice and straight and they're not touching each other to make sure there's no shorts. So now we've got our input and our output capacitor connected between the input and the output pins and the ground pin of our LDO. So now the LDO and the capacitors are all set up. All we need to do for it to run now is to connect the battery to it.
Right.
So for this, the ground pin, I'm going to use this black wire. Black is usually the standard color for ground. And that goes and connects to where all the other ground pins are, which is in the middle of the LDO. And for that, we're going to connect just further across the board, just like that. It can go really anywhere. The second pin we're going to connect is the input from the 9-volt battery. And that I'm going to use this white lead for. So the input pin connects, as we can see in the diagram here where it says input, that connects to both the capacitor and the input of the LDO. And that again, since we're looking at the flat side of the LDO, is on the right. So we can connect that to the same row that all the others are on, and then that can go down to a separate row further down the board. So now we know that this pin is the positive voltage from the 9-volt battery, and this pin is the negative voltage from the 9-volt battery. So the final wire we use is the brown wire here, and this is going to represent our output voltage. Normally, to make a little bit more sense, you might use a red wire, but in this case I've got a brown. It really doesn't matter. It's entirely up to you what color you want to use. So for this wire, we're going to connect to the output pin of the LDO, which again was on the left side if you're looking at the flat side. So we'll connect that to there, and then this we can connect elsewhere on the board. So now we've got our whole circuit set up. This is all we need to convert our voltage. So we've got our 9-volt battery, and we've got our battery connector clip here, and this goes on the top of the 9-volt battery. And now the red wire from this battery snap is a positive, so that connects into the same row of 5 as the white wire that goes into the positive input for our LDO. Just like that. And then the black wire from the battery is the negative from the battery itself, so that connects up to the negative port on the output of the LDO. And then the last thing we can do is we can turn our power on. So now our LDO will be outputting voltage, will be regulating our voltage, sorry, down to 5 volts. So the last thing we want to do is we want to get our multimeter, just here, we'll line that up somewhat like that. And we want to turn our multimeter from off to one that says, it says the V, and then it's got a line and some dashes. That indicates the flat line, indicates that it's DC voltage. If we use the V with a wavy line, it's measuring AC voltage. Now AC voltage is like a wave, whereas DC voltage is just a standard, like a flat level. Batteries output DC. The wall socket in your house outputs AC, and it's much more dangerous, so try not to play with that. So we can measure the output from our LDO. We can connect one of the black lead here, which is our negative for our multimeter. That will go to the center pin of our LDO. And then the positive is our output, and that will go to the output from our measuring. And we can see here it outputs exactly 5.00 volts.
That is very satisfying.
So we've managed to turn our 9-volt battery into a 5-volt battery.
Awesome.
Glad that worked.